now. All right, welcome back. We are INFR2350. That's Intermediate Computer Graphics in the winter 2021 semester at Ontario Tech University, and it's week 7, part 1 of our broadcast, Intro to Shadow Mapping. So where are we? We're here, week 7. And there's a couple things that were supposed to happen this week that we're going to defer, no pun intended. Notice what's happening is assignment 3 was supposed to be due this week, but last week when you were supposed to have your tutorial, that didn't quite work out the way it was supposed to. So when I was speaking with Nick, we kind of decided that we would move out assignment 3 due date till next week, give you an extra week so you can meet with Nick this Friday and talk about your in-class lab exercise, the ILE that you're going to be doing with him, as well as I won't release lab 4 or assignment 4 until then as well, till next week. However, what's going to also happen is further down the line, lab or assignment 4 was due week 11, and now I'm just going to make it due at the end of the month, at the end of the semester. So that way it'll give us a little bit more time. I'm going to push everything out 1 week. And what this will do is it'll give you a chance to learn about deferred rendering, some of the questions that I've had today, as well as about shadow mapping, which is a challenging topic that Nick is going to be dealing with starting this Friday. Okay, so that is the challenge. Also, I've released in-class exercise 3 that is going to be due on Saturday. So that is something that I want you guys to work on. Okay, so assignment 3, deferred rendering and post-processing, that's the due date is moved to Sunday, March 14th, and it's updated on Canvas. So please take a look there. All right, any questions around that before we move on? Okay, let's continue. So let's talk a little bit about shadows. So what is a shadow? The absence of light, we could say, right, on a surface. It could be, when an object occludes a light or gets in the way of light and another object, it creates a shadow, a dark area, right, where the light does not exist. Sorry, sometimes when I think about this kind of definition, I'm thinking about, some kind of superhero that can slide in and out of shadows, and that's where they live. Let's talk about shadows. So one of the things that we use shadows for is this kind of immersion effect, right? We can kind of look at a 3D object. Here's the same, kind of tennis player here in this image. You can see that there's several frames here. And here, without shadows, it's really difficult to understand where on the tennis court this player is. Are they high up on the tennis court? Are they touching down on the tennis court? Just this one here. But then as you notice, depending on where we move the shadow, right, how the shadow distance is, it really gives us a sense of height, right? So where the object is on kind of in the field, right? I'm just going to pull up a little Unity project to illustrate this, right, that I put together for today, right? So here's your basic Unity project. And there literally is one little character on the scene. And this is, from our friends at Mixamo, right? So here's our character. It's a little ninja character. And you can see here that he's got some shadows, right? But if I go to the player and I go to his skinned renderer and I turn off shadows, so I turn it off. Now, look at what this guy looks like now. It's kind of, maybe you can tell that he's on a plane, maybe not, right? But at the end of the day, it becomes a little bit more challenging to look at. So take a look at that, right? So very simple, taking shadows away, putting shadows back. Let's see that shadow effect on him again. So put on the shadows again. You can see when I put the shadows back on, right, it looks like he's, well, a little bit better. Now the surface also is a problem. The surface, this material that I'm using right here, right, is diffuse. There's no real surface area at all. It doesn't look like it's moving and anything like that. So without shadows, it does look like he's floating, doesn't it? Right? as he was poorly photoshopped. He probably was, but it's pretty cool. Let's take a look at him as he's right in there. It's not bad, right? So when I play the game, this is where it's really the effect, right? So here's the effect. Let's say it's an endless runner game. So you can see that the shadow is moving with him, right? And then if I press the spacebar, let's say, for example, that there's something that's coming at him, some kind of block, he's going to jump over it or whatever. And you can see that he gets a sense of depth when he does that. Okay, let's take the shadow away. And let's see what happens when we take the shadow away and what happens now. Okay, cool. So here's the shadow away. Do we really know that he's really running? Same character, no shadow, right? Doesn't look that great. It doesn't look, we don't even know where he is. We don't know if he's floating, is he running. We think he's on the road here or whatever this thing is, right? But we don't have an idea. But as soon as we add shadows back on, right, as an example, it gives us that sense of realism. Okay, so that's the idea that we want here with this effect. That's what the main reason why we want good shadows is, to give us this effect of realism. All right, so again, it's definitely something that can help us with depth perception, because you can see that depending on how the shadows are, not just shadows, kind of on the surface, but also from a shading perspective. That's also something else that shadows provide, a sense of depth, right, on an object, right? So you can see, we can see where the shadow appears closer to the ground. The shadow is darker, right? These are, we're just talking about things about shadows. So about shadows, what are they? Kind of thing. And we're always whenever we try and make video games, we always look to the real world to try and get an idea of what we can borrow from the real world, right? So what affordances can we bring in to a video game from the real world, where our players can look at the game and go, I understand what that is. I've seen shadows in the real world. Hey, look, I got shadows in the video game. It's more realistic for me, okay? So you can see that here where the shadow is less dark and it's farther away from the ground, it's, it gives us that sense. And again, this comes right from, kind of Art 101, drawing shadows. Again, what about the spheres? We just talked about this. There's a bunch of spheres. You can see that this could be just like we did with the little ninja character. It could be on a plane, or it could be floating, depending on where the shadows are placed. The exact same image, one with shadows that are here, right next to the spheres, one with shadows that are here, and it can create an interesting optical illusion, right? Speaking of optical illusions, right, A and B, right, depending on the shadows that are used here. Now, this is an orthographic object here, but depending on the shadows and the way that the shadows are used, it could make it so that these two objects look like they're different colors. But actually, if you look at the object again, and I'm just bringing in these two lines, you can see that these colors are the same, and so are these colors. So even though they're the same, it looks like they're different when they're farther apart, depending on the way things look, right? It really gives us a sense of not just color or shade, right? But it really gives us a sense of realism. Again, same shade, different position, different shadow values, and you can see that they're the exact same. So we get this really weird optical illusion. Other places where shadowing is awesome, especially when it comes to realism, think about things like hair. So here's without shadowing, here's with shadowing. Again, a much deeper and more realistic view here than here, right? So again, things for visual cues for humans are things like shape. It helps us with shapes, the light position, where the viewer is. Depending where the viewer is, it's going to give us a sense of if it's of depth and so on. Surface orientation, which is really important, as well as material properties, right? So how the shadow falls in the material, and if there's any kind of reflections or those kind of things off the rest of the material, right? So that kind of stuff is, again, it gives a sense of realism. So here is a little video I recommend you take a look at. The video, and I can't play it because I'm actually on YouTube. So playing a YouTube video on YouTube, bad, right? But it actually shows you a little shadow game. I'm not sure if you can see in the background here, but if you watch the video and if you download the little PowerPoint that I've put up, the video actually shows you a And let's see if I can do that without sound. And if it has sound, then I'm going to get in trouble here. So here it is. So you can see the video as an example. And the game itself that was made to work on the shadows themselves. So it's kind of a neat game. And actually, I've seen a game like this at Level Up. There was actually a game at Level Up just exactly like this, where the character would move on the shadows of an object as opposed to the platform themselves. Kind of a neat thing. So shadow physics, it can be used for that thing as well. So kind of a neat experiment that was done. Let's talk about it from a computer graphics point of view. Think about a ray. We got a bunch of rays shooting out of a light source, right, as an example. And when the light source L reaches a point P, so the ray from the light source, without encountering any scene object, so think about it, some kind of game object in the scene, right? And we can call these scene objects blockers or shadow casters or occluders, whatever you want to call them, right? So something that's in its way. If it's nothing that's in its way, P is considered lit. If I look at that pixel coming from the light, right, as an example, then that pixel will be lit. Otherwise, if there's something in between, there's shadow. That's what it is. That pixel, if we just draw that line, the pixel that is hit by that ray, if it's hit by some other occluder first, as an example, that pixel is in shadow, the one that's behind the ray. Okay, that's kind of what it is. And you can see here, this is the rendering equation introduced by Kajiya in 1986, where we only care about the direct light from the source. So think about ray casting, and that's really what it is, right? So again, there's different kinds of rays and different kinds of light sources. So there's directional light, which is like the sun, right? Point light, which really it travels in all directions, right? Sometimes we can also see spotlights that do this, right? Some kind of aerial light that not just travels in more than one directions, but almost like has additional width to the light source. And it creates both an umbra, which is the shadow area, and a penumbra, which is a lighter area in shadow. Okay, so we're going to talk about those terminologies in a second. Again, we're just literally talking right now just as an idea of what everything is. What are shadows? Kind of thing. Because we need to understand those before we can actually understand how to create shadows in a video game. A lot of times what we want to do in CG, remember guys, is mimic what we see in real life to some degree. And we have to do it we want to take it as far as it's good enough. Okay, I want to say that again. Because if we can take the realism very, very far, but the more hyper-realistic a scene is, the more computationally expensive it becomes. And the more computationally expensive it becomes, it's more challenging for us to use in a video game. Okay, so it has to be realistic, and it has to be something that is good enough for the game that we're making. Let's talk about that terminology again. Again, let's think about the umbra. So when you look at the umbra, this red area, if there's a light source, and we have some kind of occluder or blocker or something that's in the middle, a game object, right? The light source streams through. We can actually draw direct lines from the light source to across the occluder. Anything that is hitting the light source first, rays that hit the light source first, stop at the light source, right? And then we can tell that there's something between the light source and the plane, if you will, that is supposed to cast the light on. So let's suppose I'm supposed to cast light on this plane, right? But there's something in between that plane and the light source, the occluder. My ray detects the collision between the light source and the occluder and knows that it's going to cast everything that's underneath or behind the occluder in shadow, right? So it's going to make that area dark. Okay, and now depending on the kind of quality of shadow you want to create, you may have a penumbra and you may not. Okay, there are different kinds of shadow, one that has a gradient and one that's completely black. All right, so here's an example of a shadow that's been cast and there's no penumbra. Okay, just an umbra, which is where the shadow is, right? So again, you've got this thing called the shadow cone. and it's a truncated, a pyramid, if you will, from the spot that the light hits the object all the way down to the plane, all right, the receiving plane. So we have a sender and a receiver. One thing I want you to think about as well is the way the camera looks at objects as well, right? If a camera is looking at a scene, okay, so it's kind of taking in the scene, and whether it's in real life or whether it's in a video game, and if the camera has something in front of it, anything behind that something, that game object, let's say, as an example in a video game, the camera can't see that object, right? It's blocked because there's something in between it, right? And so the camera doesn't render that object. It only renders the object that it can see, right? That is unblocked, that is not occluded. And so this occlusion, right, what we call the object that's not drawn is occlusion culling, or we want to call the scene, call the areas of the scene or the objects that we don't see. Sometimes also, we also don't draw, many times, the back face. We don't see the back face. If I can't see the back face of an object, I don't draw it. I cull it, right? Why? Because if I was to draw or try and render or calculate the back face of an object, it's additional computational or computations I'm doing every frame, and I don't have to do that. So this idea of occlusion is not new. We've been using it throughout the time that we've been using computer graphics, right? So again, the one other thing that we have to think about is the distance from the light source from the source, the emitter, to the receiver. So for example, let's say the receiver is a plane, like in this case, the farther out the light source is, the shape of the shadow, the umbra, is going to be different, right? It's going to be shorter the farther away an object is. Again, this is in direct being perpendicular, right, as an example, to the plane. So 90 degrees to the plane is what this looks like here, right? So whereas if the light source is closer, the shadow becomes bigger, because think about us drawing a line from the source all the way to the receiver, right? Here's the receiver at the end, right? And anything inside of this area here would be black, okay, or dark. So shadow maps, we got to talk about shadow maps and what they are. So think about a shadow map then as an area, because really what we're doing is we're converting, we've got two things. We've got the image plane, right? And then we also have where, the camera or the eye space is, right? We've got a light source, and then we've got this shadow map. And the shadow map is basically going to tell us, it's going to produce a projection, right? From, again, depending on how far away the light source is, from the light source onto the receiving plane. Okay, that's what it's going to be doing. Okay, so it's a projection. And it depends on the angle. So if we see here that the angle from this light as it passes through, the shadow map all the way down to here, you can see that there's no occlusion by a shape like this, as an example. And so this entire thing is lit down in here, right? Because there's nothing that goes in between from here to here, as an example, if the angle of this image. So on the image plane, it's going to show up completely lit. But what about in this case? In this case, as it passes through, you can see the rays don't quite pass through all the way to the receiver. So this image is in shadow. Okay, or this part, these pixels here, back here, are in shadow. Okay. So what about shading? Well, really, it's this idea of the light, right? How the light is received from an image, right? So when the light is received from an image, as an example, and depending on the shape of the image, it creates a shadow, right, around the area that is partly occluded, right, from the object itself. So the object itself creates shadows. For example, take a look at your hands. I'm not sure if you're in a lit room, as an example, but your hands, chances are not fully lit right now, right? The reason why is because it really depends on where you are and what's lighting like in your room, but your hands might be partly in shadow. They're the light is hitting your hands or an object that you're holding or whatever right now, and part of that object is lit and the other part is in shadow. So it's the same thing. So depending on the angle of the light and the angle from where your eye is, it's going to create that shading effect. That's important. Let's take a look at Shader Toy as an example. Now, one thing to note is I decided not to use Shader Toy for our in-class exercise today because I think there's a lot more value in doing a bit of a microblog, which is something that I'm going to get you guys to do for the in-class exercise this week. All right, so take a look here. So you can see that now this is using ray marching and so on as well. And you can see what's happening. You see as the light source, this is the light source, right? As it changes position, right, you can see how what's happening is any area that's occluded, when it becomes up here, obviously there's going to be more occlusion, right, of this area here, and it starts casting shadow right there. See how it's kind of going from there all the way to the source. And also how the shadow moves around the object that is also occluding something back in here. So shadow is going to move according to this light source. Okay, now this light it's a point lamp, and it's kind of, remember, a point light is broadcasting its light in all directions, right? Point lamp. So if you wanted to fool around with these values, I encourage you to try and see what the effect is going to be when it comes to the shadow that you're going to see, right? You can also swap out some of these materials. Again, this is not for marks. This is just for your own learning. But I wanted to kind of share with you something that was shared with me when I was learning. Okay, so take a look. All right, so that is some examples from Shader Toy. So there's two types of shadows, right? There's hard shadows and there's soft shadows. Okay, let's take a look at our ninja again before we move on. So here's our ninja, right? And let's take a look at the shadows that are being cast here, right, by our little character. Would you say that these shadows are hard shadows or soft shadows? And what's the difference if you were going to talk about this, in terms of, just from an analysis perspective? What do you think? Hard shadows or soft shadow? Let me just take away this. I'll stop clicking on them so you don't have that annoying outline. What do you think? And you guys can put it in the chat. Hard shadows or soft shadows? Soft, because it looks blurred around the edges, Andrew says. And I think correctly, that is exactly it. All right, so let's see if what happens is if we want to make the shadows cast. First of all, he receives shadows as well. If I turn this off where he doesn't receive shadows, right, you can see that there is a bit of an effect. So here is no shadows. He's not receiving shadows as well, right? So you can see that there's a bit of, and I'm not sure how this comes out for you guys, but you can see there's a bit of a belt that you can see there, right? If I click he receives shadows, that goes away. The detail goes away because of the direction of the position of the directional light. Okay, the directional light in a scene again acts like the sun, right? So depending on the orientation of the directional light, let's suppose I made this at a different angle, you can create a sun-like effect where if I draw the angle further out, right, you can see that the scene gets darker, his shadows drag on, because the directional light is an orthographic object, right? It makes his shadows, it kind of projects his shadows from a certain angle, right? And again, you can see that there's two angles here. One is at -30 to the y-axis, which is kind of up. And it's also angled across the x-axis. So if I keep going, you can see that the light, the scene will turn darker and darker until it's completely black, right? And then if I go overhead with the directional light, for example, if I go further and further kind of above the character, right, or maybe even in front of the character, let's light him from this side this time, just to create a different effect, right? You can see that now we can see the character's face in more detail, but his back is in shadow. Let's continue to look at that shadow for a second as we change it. So the way it works in Unity or in any commercial game engine, which we're going to learn about in next semester for you guys in game engines, right? As an example, is you can change the quality settings of an object like this to change the way the light and the shadows are being projected, right? So again, if I was to look at my project settings, and you can do that if you are familiar with Unity or not, you can see that the quality settings right now for PC are ultra, right? So that's what ultra is. Now take a look at the shadows over here, right? So notice it says hard and soft shadows are something that I can receive. They can change the quality settings, right? I can also just say disable shadows. So there's no shadows. I can do that from the entire game. All objects in the game don't have any shadows anymore. And only hard shadows. Take a look at that hard shadows now. There you go. That is an example of hard shadows. Okay, now if I was going to just use hard shadows in the scene instead of soft shadows, by the way, it's hard shadows everywhere. I'm just going to park project settings up here for now. But let's suppose I was to play the game now and I did the same thing. Take a look at how the hard shadows look. By the way, I'm also doing it from with a different angle of the sun. So let's move that sun, the directional light, back to where it was. It was about 50 degrees. There we go. Here's the directional light. So if I did this again, and if I was to move it, you can see now how the hard shadows, did the hard shadows look worse? What do you think? So here's the hard shadows. Do you think they look better, worse, the same? Very pixelated. Ryan says he likes them better personally, right? Noah says it looks worse. Some of it is, I have to tell you that it really depends on the type of game you want to make. Sometimes you want to make shadows look like this. Really depends on the game that you're playing, right? You know, if you want to make it a hyper realistic game, then obviously this is not a great idea. But what this does, the reason why we want to use hard shadows instead of soft shadows, is that hard shadows are less computationally expensive than soft shadows. Why? Think about the ray again. Think about the umbra and the penumbra. There's no penumbra here. It's pure umbra. That's what it is here. And there's no anti-aliasing, right? And we're going to talk about the problems with shadow mapping in general later on. But this is the kind of stuff that we have a problem with, right? Where this doesn't look as realistic as, if I go back to project settings and I change it back, right, to hard and soft shadows, right? Then let's take a look at that. That looks a little bit more realistic. The other thing we can do with the shadow mapping is we can also change the shadow distance. That's also something. And there's something also called cascade splits. And this, by the way, it doesn't matter whether you're doing it with a commercial game engine or you're using cascading shadow maps, which is what we're going to talk about later on. If I say no cascades, so there's no cascades for the shadow maps, right? And if I go back to my scene, take a look at that. There's no cascades for the shadow mapping. Things become a little weird looking, right? Don't they? You get some weird jaggies, some really weird artifacts that happen here with the shadow, right? But as soon as I turn back, let me just pull this over here so we can do it at the same time. As soon as I turn back on the shadow maps, all right, so how many cascades do I want? Right now there's no cascades. If I go to 2 cascades, again, take a look at 2 cascades. There's still a shadow, but it produces kind of a weird effect. Once I go back to 4 cascades for this type of work, it becomes much more detailed. So think about what a cascade is, and we'll talk about cascaded shadow maps later. The farther an object is away from you, the less detailed the shadow is supposed to be. I think that's the general idea behind cascading shadow maps, right? So you can see the split here, right? So different splits, the closer it is, the more accurate or sharper the shadow is. The farther it is, the worse it is in terms of quality. Why? Because we don't really care about something that's far away. We care about something that's closer to the camera that we can see, okay? Something else you can play with a lot is the shadow distance. And this doesn't matter whether it's a commercial game engine or your own. Let's suppose I change the shadow distance to 10. Take a look at that, right? Look at the detail that you see here in terms of the sharpness of the lines. I'm going to ask you again, is this a soft shadow or a hard shadow? Take a look at that shadow. I just changed the shadow distance, right? Hard shadow or soft shadow? Is it the same? What do you think? Can you tell? I'm pulling this out. It looks harder because of the harder element, but it actually is a soft shadow. It's just the distance is different. And if you play with this value, so as I increase the shadow distance away, take a look at what the process, what it does for us as I increase the distance. The more I increase the distance, and if I keep going, right, the blurrier it starts to look, right? Blurrier and blurrier and blurrier until it becomes less sharp. We want it to be less sharp because if it's super sharp, let's say, for example, if I take the shadow distance down to 0, there's no shadow. But as soon as I start increasing that distance, take a look at that. It becomes almost like a decal, right? Like as if I'm painting the shadow directly on the ground. There's a shadow distance of, let's say, 4. Now, if I kept it 4, look where the camera is. The camera's way out here, right? That means in the game, no shadow, right? As I move the shadow distance is something that's reasonable for the game. Let's suppose something like a value of 10. Remember, it was a 150 before. What about if I play the game now? What is that going to do with the game? Well, it's okay, right? The further the shadow distance, the less defined the shadow is and maybe more realistic, right? The further the shadow distance, right? More realistic. It makes sense to see how it works. This doesn't look quite right. It almost looks like there's 2 characters here, right? And by the way, this is the shadow distance for everything in the scene, not just the character, because I'm messing with the quality settings, right? Let's go back to 150 and see what that looks like. Again, do you think that's better, farther away? Or do you think that's better, closer up? So again, it's up to you and the way you have it. That's right. Jaden says, kind of looks like the character is shadows another character because it's too sharp. Even though the resolution is what it is, it looks like it's too sharp. Let's go back to 150 for a second. And notice also there's something called anti-aliasing up here, right? When it comes to rendering. What if I turn anti-aliasing off, right? So here's no anti-aliasing at all. Well, let's take a look at the scene. So if I zoom in at the scene while what the scene is playing here, all right? And again, we're just using this as an example. No anti-aliasing. Okay, cool. Anti-aliasing is off. Let's make sure that that's true and run it again. Because sometimes, yeah, I thought so. The settings were not applied. Let's go to disabled here. Sometimes you have to disable them. And let's not use soft particles. We'll use hard particles as an example. There's also called a distance shadow mask or a shadow mask we can turn on. We can really reduce this a lot more. And let's just do it one more time and see if there's a difference. Probably not. Okay, it's hard to see anyway. But the idea is that this is where, again, no anti-aliasing, right, as an example. We're not using soft particles at all in the scene, which we don't really care about. And you can see that we're using a shadow mask instead of a distance shadow mask. Here's a shadow mask, distance shadow mask. Let's move this to 150 and see the difference. Distance shadow mask, shadow mask. You see the difference? Not really. One is just a more of a performance mode more than anything else. But where you really see the difference is this. If I go to hard shadows only, here's hard shadows only, where I go hard and soft shadows, and where I change my shadow resolution. So low resolution shadows, right? There's low resolution. Again, the same distance, right? There's medium resolution, okay? So we see a bit of jitter, a bit of artifact here in the shadow area, right? And then we go to high resolution, right? So a little bit of some anti-aliasing and a little bit of penumbra around the area here, right? And then if I go to very high resolution, it's super sharp. Very high resolution with 4 cascades at 150 shadow distance. Try and run this on your cell phone. It's not going to work very good, right? And let's turn anti-aliasing all the way up to 8 times multi-sampling with soft particles, right? Yeah, it says it needs deferred rendering. All right, so that's enough for this little ninja. But I wanted to give you this idea, right? This idea that, you know, especially with motion, right? This idea that we have light and shadow and how it bounces off, how it works, okay? So again, we've got the camera, we've got the image plane. the object is going to be converted from a 3D object into a 2D object on the image plane that we can see, right? We're looking at a 3D object, but we're converting it to something that we can see on a screen, right? We have shadows that are reflected, again, from the light source. So we have shadows that are created from the light source, and the view ray, which is coming from the camera, is hitting the object, and depending on the angle that the surfaces of the object are reflecting back to the camera, or seeing it or being seen in the camera, we've got more or less shading. All right, so again, we shoot from the eye, ray hits a surface, sends shadow ray out to check if the light reaches this point. If the shadow ray is obstructed, then the point is in shadow. Otherwise, the point is lit. Okay, and here's the way you can tell. All right, so hard shadows. Soft shadows, on the other hand, have both like we said before, an umbra and a penumbra. They're more realistic. The light source is treated more like a physical object. They're more like cones now, as opposed to rays, right? So that's a little different. So you have a bunch of rays shooting out all at the same time. And what ends up happening is you get more of a gradient effect around an object. Again, think about our little character that we just saw, right? Where we had a cascade or where we didn't. So when do we use hard shadows? And here's, again, hard shadows versus soft shadows. Again, both are using, this is using a point light source. This is an area light source. It creates a different kind of shadow effect. Some basic algorithms, all right? There's different kinds of algorithms. Planar shadows, again, these are all hard shadows, shadow maps, and shadow volumes. Those three things that we're going to be talking about, all right, today. So let's think about planar shadows for a second. So planar shadows is exactly what it sounds like. You have a plane that's receiving the light, all right? And in between the light and the plane, like we said before, is some kind of occluder, right? So that's the planar surfaces. The shadow gets cast on a planar surface, and basically what we're doing is we're projecting, the extents, if you will, of the object that you see in the scene here. The extents, you're creating a projection from the edges of the object down to the plane. Okay, that's what's happening. Okay. So bad things about planar shadows. Offset in shadows, it's due to depth calculation. How to fix that? We can turn on or off the Z buffer, right? So we can change the way it looks. Shadows may fall outside of the receiver. How do we fix that? And the receiver being the plane. Draw the receiver and then update the stencil buffer is a way of doing that. Shadows have to be rendered every frame. Solution, we render into a texture, deferred rendering, right? And this is why we want to use deferred rendering with shadow mapping, because then what ends up happening is we can render to some kind of off-screen buffer, right, as an example, and then that off-screen buffer gets rendered to a full screen quad, right? And that's how we can do not just shadows, but also post-processing effects. And what about restrictive to planar objects? Well, we really can't do much about that. All right, so that's when it comes to limitations about planar shadows. How about shadow volumes? So this is kind of interesting. It was invented way back in '77. It was really popularized in the game Doom 3 in 2005, right? And really, it's a volume of space. Think about a volumetric area, right? And it's formed by an occluder, right? So whatever the occluder is, it forms that volume, right? And any object inside the shadow volume is in shadow. So it's almost like it creates another mesh, right? And that other mesh is something that is, and take a look at that image on the right here. That mesh, right? Anything that is in that blue area that you see here is in shadow. Anything that's in this, kind of other area here, the not blue area, I'm not even going to venture to guess the exact, a color there, magenta maybe, right? Is not in shadow, but actually is lit. Okay. So that is something that we use when we talk about shadow volumes. Okay, so that's another way of doing it. One great thing about shadow volumes is they can, you can have more than one of them that interact to create multiple shadows. Back to our character in Unity, right? As an example, if I had an additional light source here in Unity, let's add a light to the scene. So let's go and we'll add a light. Let's add a point light somewhere in the scene, right? So let's say the point light now is going to be maybe behind the player, up above here as an example. And let's take a look right now. By definition, when I kind of enter an object into the scene, like a point light, right? The point light has a couple of things here, right? It has an intensity and a range. Let's make the range really big, right? So big point light. And let's make the intensity really big. And let's make sure that the shadows are cast. So we'll cast hard shadows so we can see what that looks like, right? Again, you can do it per light. And let's change the color to make it something that we can see like red. Okay, so that's interesting. So we can see that this material on the plane, right, as an example, when it comes to lighting, casting shadows is happening, receiving shadows is on. But here's our point light, and not really seeing an effect of the point light. Here's, as we get closer, here is the light. Take a look at how that it's lit up here with the point light, but we don't see a lot of shadows. Well, one of them is because of the distance, right? That's one thing to note as well, right? The point light itself, we can change the scale of the point light, and that's the range. So if I go to the range, if I change the range to something like 10, closer, you can see that that's far enough away that this character doesn't receive light. Once I go to something like 50, then the character does receive light, and it's quite bright, right from this angle here. And when I play the game, you can see the light source is there. It does affect the shadows that are on the character. It lights them up nice and green, but no shadow, no lights there. What about if I add, instead of a point light, let's change it from a point light. Let's call this, we'll rename this thing to a light. If I can spell properly, light. Okay, and let's change it from a point light to a spotlight. Okay, so spotlight has a different kind of shape. It looks like a cone, like we talked about before, right? And let's suppose I go into the transform and I want to do some rotation on the transform. So here's we're rotating across the x-axis here, right? And one thing to note also, it's kind of hard to see, but when you're in 3D, one of the challenges that we always have is that the light isn't physically, even though it looks from that angle that it's on the scene, as an example, it may not be. So there's our green light. Now, a point light shines in all direction, right? But a spotlight does not, right? Spotlight only shines. It kind of creates light only in the area, as an example, that it's affecting. Let's just change the range of the spotlight to 20. Okay, maybe make it 30. There we go. And let's change the intensity. The intensity is pretty crazy. Let's make it so it's like, I don't know, 4. Okay, so you can see that this is something that we want. We want it in real time. The indirect multiplier can stay the same. We want hard and soft shadows. So we want both hard and soft shadows. And this is the strength of the shadows to 1. Let's go back to our player by using frame select mode. Right, and you can see here that when we do it, we have 2 shadows. One, there's the occlusion of the green light that's coming from behind the player, as well as this shadow here that comes from the directional light. All right, so both those 2 lights are interacting at the same time. So if I press play now, you can see I can see kind of, my camera's in a weird spot, but you can see kind of that I have both shadows happening at the same time. By the way, the more light sources, this is where light sources come into play. The more light sources I have in a scene, again, more than 4 lights or so, right, you're going to have, the scene is going to become more computationally expensive and it's going to start bogging down. All right, so different light sources is what we're saying there. We can see different light volumes, and then that's how we would do a spotlight anyway. We use some kind of shape, like a cone, right, as an example. And then what we want to do is any pixel that's inside of that light volume that is not occluded by something else that comes from that light volume. We have an emission from the light volume and a receiving area, right? The plane. Anything that comes in there is not occluded, and so those pixels are lit. Okay. So that's how it works. Here's the eye, and you can see wherever the eye is, or the camera, you can see that any area here, think about the eye as the visibility of the light source, right? I also like to think about the light source in this case as almost like a frustum of its own. It creates this truncated cone idea, or truncated prism or pyramid that comes from the light source, like an eye, and that kind of whatever the light source can see. By the way, as an aside, think about using line of sight with a frustum for your enemy characters, as opposed to a ray. Sometimes we use a ray for a line of sight, as an example, when it comes to creating an AI. But we can also use a frustum. Okay, so cool. So shadow volumes again. Here's that truncated pyramid. Again, if we're going to hit something like a cube, and the truncated pyramid, or in this particular case, creates a shadow volume. And anything that's inside of the shadow volume, we can use different ways of doing this. But any pixel that's inside here, any object that is supposed to be rendered that's inside here would be in shadow. Okay, any object. Okay, even some parts of, depending on how perpendicular this is from the actual cube, its own faces would also be darker in shadow, right, compared to the top face. So each especially the side faces and so on. Okay, so anything that's in the shadow, that's shadow volumes. We can also have multiple light sources as an example, and we can also have a light source that's been, you might have multiple shadows. Let's say, for example, this is the plane, the receiving plane, but we have multiple sources. Let's suppose I have a shadowing object, an occluder, right? And I create several areas that are lighter and darker, depending on how many times the object is occluded. You can obviously see here that there are 3 different objects here that are occluding the light or the pixels from reaching this plane back here. But again, one thing to note is if you draw a line from the light source all the way to the receiving plane, it may not make a difference. Or it really also depends on how much these objects occlude. Are they transparent objects or semi-transparent objects that are letting some light pass through? Are they fairly opaque objects? It can all make a difference in the back end over here. Right. So let's continue. Again, we're just talking about light. So how would you do shadow volumes? You'd use a stencil buffer, right? And remember that this allows, kind of us to decide, or it kind of creates a test whether to discard a fragment or not. That's what it does. This is actually not worded great, but it basically creates a test, right? That's what it does. Creates a test to see whether to discard a fragment or not, right? What is it? And what does it mean if the test passes or fails? Well, if it fails, then what ends up happening is then we discard part of the fragment, and you can have 2 things. We have a depth test, right, as an example, as well as a stencil test. And depending on when you use one or the other, right, if the depth test passes, right, as an example, then the fragment continues through the graphics pipeline and the stencil operation for the stencil. So both those 2 things. And so both are applied, right? If the depth test fails, so I can't see, the plane that I'm targeting, as an example, then the stencil operation for the stencil passes, but the depth test fails, so that I don't create light there, but I do create that area that I show that's in shadow. Okay, so that is shadow volumes. Let's think about shadow maps for a second as we move on. Shadow maps are interesting. There's basically 2 passes when it comes to shadow maps. If I'm creating a map, think about a map as a texture, all right, is what I'm going to be creating, right? So, so I get 2 passes. The first pass is really, I'm going to get the scene rendered from the point of view of the light. Okay, so here's where the point of view of the light is, right? And only the depth of each fragment is computed, all right? So that's the first thing. And then the next thing is, the scene is rendered as usual, but with extra tests to see if the current fragment is in shadow or not. So 2 passes, right? And that creates your shadow map, all right? So the distances are stored in a texture. The texture is the shadow map, right? And then you're comparing the texture. You're almost like, if you want to think about combining both textures together in a post-processing step to create your shadow. All right. So rendering the shadow map. All right. So things to consider. The field of view of the shadow map is important, right? So again, think about the light frustum. Again, the light frustum, depending on what that looks like. So the effect the light is going to have for each pixel in the scene, as an example, can create things like Z fighting and sampling problems. Okay, we'll talk about that again. Again, pass 1, we're going to say this a couple times. Render the scene from the light's point of view. Pass 2, render the scene from the camera's point of view. So what does the camera see, right? And here's what it would look like. You want to create a 2D texture using a frame buffer's depth buffer. And then we're going to generate the depth texture. And there's something I wanted to show you here. This is a kind of a neat little example. If I'll bring this to you guys in a little bit of this one here. I really love this one when I saw this the first time. Let's go back to this. So what you can do with this is in real time, it uses WebGL. And what I can do is I can drag the light around, right, to create the shadows, right? So that's what the light does. So I can move light. I can also move the camera so I can see the scene. Again, this is in real time. You can try this out as well. You can see the scene in real time. And then what you can do is you can show the depth map only. Take a look at that. It's kind of neat, right? Where the depth map itself, right, creates, it changes. This is what we're talking about when it comes to depth map, right? So look at the objects that are in the scene, right? Let me go back to the scene itself, right? So here's my scene, and that is this texture. There's a texture here that's being created in real time, right? Every frame, the shadow map is being rendered. Some of it's pretty bad. Take a look at that over there. So hard shadows. Again, this is done in WebGL. So there's some limitations on, or at the time, there's some limitations on what this can do. It's kind of neat thing, and this tells you, kind of shows you what you can do, and also gives you some examples of light and shadow. All right, shadow mapping. So again, different lights produce different effects. So again, the directional light, like we saw earlier on Unity, it uses an orthographic projection. Right, so depending on the angle, that is how the shadow or the shadow map is going to be created based on the angle of the directional light. And we got to think about the directional light as an object that's infinitely far away, right, like the sun, that creates a light that comes streaming in from one direction all the time. Think about this as our environmental light more than anything else when we're outside. Okay. And a spotlight, it uses a perspective projection, right? In that wherever the spotlight comes from, we have this volume of light that comes out and meets all the pixels at the receiving end, right? Anything that from the light frustum's perspective, right? And where a point light shoots out in all directions, omnidirectional. And what that does, this is kind of mostly more computationally expensive, believe it or not, than the spotlight in some ways, because it's creating shadows in all directions. So think about rays shooting out everywhere, right? So point lights are kind of weird. And think about where you would use point lights in a game. I had a conversation with a student earlier or last week, and the question that I had coming from them was, so where would I use point lights? I don't understand how that would work, right? And how does that make sense with my scene? I'm not going to say who I spoke to. But think about this in terms of what point lights are for in your game when it comes to your GDW game. How does it make sense that the point lights exist? Think about that. Where should the point lights be, and what would their role be, right? Because as soon as I put a point light into the scene, right, once I put them into the scene, it has to make sense, right? Otherwise, you're going to have a point light in the scene that's going to create very expensive shadow maps, all right? Because the point light is going in all directions. Okay, so keep that in mind. Think about what this says. It says a point light creates 6 light frustums, right? And renders to a cube map inside a geometry shader. Guys, this is insane when it comes to the, how computationally expensive this can be. Whereas a spotlight has a very directional area that only affects, the objects in the scene or pixels in the scene that it can see based on its light volume. All right. So again, let's think about shadow mapping as we continue, right? Shadow's depth, it has this 2-pass algorithm, like we said before. First pass, this is a great little article, by the way, by Microsoft, right? First pass generates a depth map in light space. The second pass, the map is used to compare each pixel's depth in light space against its corresponding depth in the light space depth map, right? So key parts of a shadow scene is light and the view camera. Depending on where your camera is, you're going to see things at a different angle and also from the angle of the light that's casting down, that also is going to play in as to how your scene is going to be displayed. So again, in the first pass, more detail, right, about when it comes to it, it's all about the depth buffer, right? So what we want to do in the first pass is kind of generate this depth buffer. Okay, so what can I see as an example? And remember, when we talk about deferred rendering, I believe next week, we're going to be talking about separating out the depth buffer from the normals, from the color buffer, into separate buffers, and then combining them into something called a G buffer, right? When we combine things into a G buffer, and when it comes to deferred rendering, we get this idea of, we have control over how the scene is rendered in a lot more detail, right? And we can use the depth buffer again to create your shadow maps. Okay, so that's kind of the process. We have our light space view, light space projection onto the surface. It passes through a vertex shader, through the whole graphics pipeline, and we kind of create, the output from that is just a depth buffer. We don't care about color. We don't care about normals. Pass 2, when it comes through the second time, we want to transform each vertex twice. So each vertex is first transformed into the camera's view space, right, as an example. So we go through that transformation matrix, and then we transform it again, right, as an example, with the view projection texture matrix, which is a different matrix altogether, right? And that second time, what we're going to get is a combination. We're going to merge together, right, the position, right, and the texture coordinate transform. We're going to merge them in together, right? And then what we're going to get at the end is a combination of color. And of course, you get your depth buffer over here. So the depth buffer comes inbound, right? And you're going to get that depth buffer combined with your texture and position to create your color and depth buffer kind of combined, right? So kind of a combination. So there's your world scene as an example. That is your base scene, unlit, right? Then you're going to use the light from inside of, kind of the scene to create, the additional information that you're going to combine at the end. And this is similar to what we do when we talk about, rendering off screen, right? We're going to kind of do this in a couple of passes, but we can do this off screen as well. And again, so-called deferred shading or rendering, which we're going to talk about next week. All right, what about problems? We've seen some problems with shadows today when we looked at the Unity example, right? Some of the issues with shadows, as an example, are things like perspective aliasing, projective aliasing, shadow acne, I love this one, right? And Peter panning, all right, which we actually saw earlier today in the Unity scene that I showed you. So what is perspective or projective aliasing? So projective aliasing is like light that is parallel to the light direction of the scene, right? And what ends up happening is it creates this really weird, we kind of saw this earlier, really weird, effect, as an example. And sometimes you get things that look like this, a bunch of jaggies, right? As an example. And so the best case is where you have an overhead light where it's a flat floor and you're coming, from a perpendicular light perspective. So that's the best case scenario when it comes to projective aliasing. Worst case is some kind of overhead light with straight walls. And that's where you get like really, really bad, you know, a really bad situation. Here is another example of that. So that's projective aliasing. Here's perspective aliasing. This is the difference between projective aliasing, where the light is coming from, right, and perspective aliasing, okay? Perspective aliasing is a little different. It's a common artifact, and it occurs when the mapping of pixels in view space to texels, right, in the shadow map is not a one-to-one ratio. And this is because the pixels close to the near plane are closer together and require a higher shadow map resolution, right, than the ones farther apart. And so what ends up happening is the one on the left, perspective aliasing, is too high, right, because there's too many eye space pixels mapped in the shadow map texels. So too many of these, right? And the image on the right is low. Perspective aliasing is low because there is a one-to-one mapping between the eye space pixels and the shadow map texels. All right, so that is what can happen. Again, a fix for this is cascaded shadow maps. Okay, that's the most popular technique to fix this anti-aliasing issue. All right, and we can see some examples of this. Here's The Witcher. Take a look at The Witcher 3. Hard shadows, right? And take a look at Assassin's Creed, right? You can see Assassin's Creed uses a much, I like this a lot more, but it really depends on, again, art style could be an issue. This definitely used to be the norm when it came to shadow mapping. Sometimes we'd even use fake shadows a lot as well, which means, especially if there is if it's kind of a cartoony-like game, think about this, right? Where if an object is walking, we can just use a blob, right? So it's a complete lie. And the blob can be basically just another texture that's hanging out at the bottom of the object, and that's modified. It's almost like the light source, the shape of the light source, if you think about it, right? You know, kind of at an angle from the light. So it creates almost like a weird blobby shadow, right? Again, some comic books use the exact same thing, where you see just a big blob underneath the character's feet to give the impression of dark shadow without doing actual shadow. All right, so that's kind of a couple of ways of doing it. How about shadow acne? So shadow acne, right, it occurs when the shadow map quantizes the depth over an entire texel, all right? And when the shader compares an actual depth against the value, it's likely to be self-shadowed as it is to be unshadowed. So it creates this self-shadowed situation where you see these speckled artifacts or moire patterns. That is an artifact, and that artifact is shadow acne or erroneous self-shadowing, right? So be careful. If your scene looks like this after you do your shadow mapping, that is not a good thing to do. And again, the solution would be to use shadow maps, right? And shadow mapping where we get, kind of two passes to do that. You can, if you didn't have two passes, then sometimes what ends up happening, or if you get the wrong information, as an example, in your second pass, it can create this freckling or speckling of materials. So be careful about that. And sometimes just values, distance from the object. We talked about a couple things, even on the Unity side, that can create this really weird speckled artifact effect. Peter panning. And what this is where we see an image on the left where the shadow is detached somehow because the shadow distance, the distance between the shadow map itself or the shadow and the object are separated, and it looks like the object is floating where it's actually not. Okay, so just as an example about this compared to this, all right? So yeah, circle shadows are the worst because circle shadows actually, let me go back. Circle shadows, they're not the worst, right? Ryan says Peter Pan is a great movie, yeah. But you know what? At the end of the day, it's a cheap effect, and if it works for your type of art style, that's okay. All right, so that is Peter panning. And how do we address this? Again, we can apply a constant depth bias, right, as an example. And during the light pass, we want to push the depth slightly deeper or lower, as an example, than whatever we get. We can play with the depth numbers that we get back. And I don't know what happened here for this slide. Goodbye. This is what it should look like. So again, how does it work visually? Too little depth causes Z fighting. Okay, Z fighting means there's two textures. The shadow map itself is inside the texture itself, so it fights at the same level, right? Too much depth causes light leaking, and light leaking you can see what it looks like in terms of here's light leakage right here, and there's acne or Z fighting. That's what the acne causes in the front faces. And then when it's shifted back too much, you can see that the shadow itself, if it's shifted forward, you can see that the shadow is inside the object, and shifted back, you'll see an area that is, you're going to get some Peter panning. Okay, so that is, shadow mapping and some of its problems. Let's think about improvements to consider. Increase the precision of the depth buffer. So the more precise the depth buffer is, the cleaner your maps are going to look. But warning, the more precise your depth buffer is, remember, you are rendering this thing every frame. You need to test for performance. You need to kind of adjust these numbers so that your game is still performant and yet be high resolution enough that it's going to be you're going to get a good map, right? The higher the resolution of the map, again, the more computationally expensive it is. And if you notice our adjustments in Unity again, or we made some adjustments even on in a commercial game engine where you can adjust the resolution, right? Again, when we think about high resolution compared to medium resolution, let's take a look at that. Or even something lower like low resolution, there's reasons for this. Depending on what this object is and how it's being hit by light, we may want to reduce it. Also depending on the hardware that we're displaying things on. If, for example, take a look at the quality index as an example for different kinds of hardware. So if I'm looking at a Windows machine, we're thinking about Ultra. But if I'm looking at an iOS or Android device, we're looking at medium. Whereas WebGL, so on the web, we can probably do high. Okay, so that is, different levels of shadow resolution depending on the platform. So here we're at, high. And some video cards can handle very high. And this is where you have settings in your video game that can adjust things like the shadows, soft and hard shadows, the distance from the shadows, and so on. There's a lot of games that have these settings. And the reason why is for performance reasons. Okay. So other issues we can see, constant bias. There's a problem right there. Take a look at how the constant bias, what ends up happening is it separates, and there's different values here that you can see that separates the the shadow from the actual object that it should be, where it should be. Notice the rest of the object is still in shadow as well. A polygon offset. All right, again, depending on the polygon offset, you can use another technique that where it's off, where here it's on, and you can see that once we add, a polygon offset, right, as an example, then you can create a different shadow effect. Again, take a look at this paper; it's really great. Shadows and CCM implementation that I've put in there for you. A normal offset, okay, which push the depth in the direction of the normal, right? Again, it's a complement to the constant depth bias, and what it does, it creates a different kind of effect compared to this. This is bad, this is better, right? And then normal shading, where we can actually create a shader based on the normals, right? Wherever the normals are, you can actually add shading around there, and it can create a faux shading effect, right, without using a shadow map at all. Okay. All right, and sometimes we also may need some additional or advanced shadow mapping, things like warping techniques, perspective shadow maps, light space perspective shadow maps, logarithmic perspective shadow maps, frustum partitioning techniques of different kinds, and all kinds of things. If you're interested more in this kind of thing, these advanced shadow mapping algorithms, you're going to learn about some of these with advanced graphics, and Dr. Hogue is probably going to talk about some of these techniques in his course. All right, let's just go back to the in-class exercise now as we wind down today's lecture. So what do I want you to do for the in-class exercise? By the way, the in-class exercise is live. right? It's due on Saturday at midnight. I wanted to give you an extra space, right? To do that. So remember, you don't have your assignment. Your assignment 3 is not due on Sunday. Just to reiterate, it's due next Sunday. So you have an extra time to do that. So you're going to create a little microblog, right? And it's about shadows and 2 of your favorite games of similar types. So example, let's say you chose, I don't know, let's say my favorite game right now that I'm playing a lot is Valheim, like I talked about last week. Let's say Valheim and Rust. Let's suppose I wanted to compare those 2 games when it comes to shadow mapping, right? Take a look at those 2 games, whatever games you want, whether it's shooters or platformers or whatever, right? Take a look at those 2 games and identify if the games are using hard shadows or soft shadows or both. Maybe they're both. Identify any artifacts you see. Do you see any kind of speckling, any kind of acne, as an example? How does the anti-aliasing look on on the shadow maps? Are they high resolution shadow maps? What are you seeing there, right? And discuss how the shadows are used in each game. Do they work for you? Does it make sense? If they're low resolution, some people have said that, I really like hard shadow maps because I like them more, right? Depending on the art style. Do the shadow maps that are used in the game, do they work for the game? Because remember, at the end of the day, it's all about the user experience, right? So think about that. Are they good or bad? And what could the developers have done differently? If you were the developer, is there something that you would change? For the games that you're comparing, it doesn't matter which games, as long as they have shadows in them, right? And they're fairly recent. So let's go back between, worst case scenario, 10 years. Okay, so we don't want to go like back to the 1980s. Something that is your favorite game, a couple of your favorite games of the last, let's say 10 years or so, that include shadow maps or shadows in general, right? And that they're same type, because you want to compare as much as possible apples to apples. So I'm not going to compare, Minecraft, to Fallout. Maybe there's not a great comparison there. Maybe, right? I want screenshots of each game to illustrate your point, things that you're talking about. Submission criteria are PDF document of your microblog, your full name, your student ID should be included. Cite any references, things like images and websites. I don't need it to be in IEEE format, so you don't have to, go up an overleaf and create a crazy document. It doesn't have to be that crazy. This could be, a page or 2 pages if you figure just adding in all the screenshots or whatever. And you want to add screenshots where they make sense. I don't want you to fill the page with screenshots. Here's my in-class exercise, Tom. Here's a bunch of screenshots. No, I want you to do some comparison, and your submissions will be marked on the quality of your writing. So please check your spelling and those kind of things. I don't expect you to be writers by any means, but if you can get clearly to the point, and the application of your knowledge as a computer graphics programmer and game designer. And what I mean by game designer is when you guys look at the game and say to yourself, does this look good? What is the user experience like for this game? Like, do I really like it? Does it look like crap? And if it does look like crap, why? What could I have done differently? So a few thoughts. It doesn't have to be very long. Please don't write 10,000 words, okay? It's got to be something within reason. And I'm going to give you some leeway, let's say. Could be as little as 1 page if you make it really nice, and if the images work great, and it could be as many as, let's say, 5 pages. Please don't go beyond 5 pages, with everything. And that way, and I'm talking about like images and your name and all that kind of stuff. And if you want to add a title page and references, that's like could be 5 pages, right? So, Andrew says, can we get screenshots online if we play on console or take pictures? Yeah, but just cite where you got them from. I'm okay with that. Like, I'm okay with you getting screenshots from wherever, but the screenshots have to illustrate your point. So if you just get random screenshots of your game, but there's no shadow, what's the point, right? Get screenshots with that really show off the shadow. So you need to search for that stuff. Please try not to communicate with other people in the class about this. I'd like to see your own thoughts around this, your own thoughts around shadows. Because remember, this is some of these things that we're doing, these in-class exercise guys, are going to prep you for the final exam. Right? Because remember, I'm going to probably ask you, there's going to be 2 parts to the final exam. The first part of the final exam is a written exercise. It could be some questions and maybe a longer answer like this, right? Where I ask you, so analyze the shadows in the scene. What do you think? Kind of thing. Could be like that. And the second exercise of the final exam, there's 2 parts, and they're take-home exams, you have the whole week to do them, or 2 weeks, however long we have for our exam period, right? The second part is going to be all around, a technical issue, a technical piece that you're going to have to write, some kind of, little assignment similar to one of the assignments we've given you right now, assignment 1, 2, 3, or 4, as we're going forward. Some little piece part, some little technical assignment that you're going to create. We're going to ask you to do an effect, right, to basically evaluate you on how comfortable you are with that particular thing, similar to what we did with our midterm test, that we did this semester. All right, so far. So similar to what we did with midterm. So kind of a mix of a midterm test, a little bit of true, false, multiple choice, and a little bit of a blog. All right, that's what's going to happen. So to prepare yourself, please don't take these lightly. These count. This is worth 1.5% of your final grade, or altogether, or 2.5% of your final grade. Take a look at these. Take this seriously, and it'll get your mind thinking about video games in a different way. All right. So, and remember, when we're developers or programmers, playing video games is good. We can relax, but I want you to start looking at video games, and I'm sure that other people have said this, other professors have said this for you. Take a look at them with your technical eyes. Take a look at them with your critical eyes, right? Look at the video game and say, what are really great parts of this video game? What are the mechanics that really work for me? What are the mechanics that don't work for me? What are the graphics that work for me? What are the graphics that don't work for me? What about the engine? What about the glitches? What could have the developers done differently? And I want you to start thinking about that, because it's going to affect the quality of your own games. All right, that's it for me today. That's all I wanted to talk about. Any questions around shadow mapping or anything else? Again, just to reiterate that your assignment 3 is not due this week. It's due next week on Sunday. That's the 14th at midnight. Okay? So just to let you guys know about that. All right. Otherwise, that's it for me. Any questions before we say goodbye for today? Guys, thank you so much then. I'm going to stop recording this one. And I'll see you guys next week. Take care.